Do you guys know the show Car Talk? If you grew up listening to public radio between the 80s and the 2010s, you probably do. It was a call-in radio show that ran weekly on National Public Radio for over 30 years. Listeners would call in, asking for help with whatever car-related problem they were trying to solve, and the hosts, who were two MIT engineers specializing in auto mechanics, would offer their humorous, semi-serious guidance on how to solve the listeners' issues. The show would usually end with a puzzler, a little one-minute riddle whose solution would be presented in the next episode. They were usually fairly abstract problems that would have a nice, satisfying solution. This is not one of them. In fact, it's not a puzzler at all, but a very practical problem featured on the show that has distracted me for about a year now. I want to go over what the problem is, how to solve it, and why it's been bothering me for so long. In episode 1045, which I'll link in the description, a trucker called in to explain that his fuel gauge was busted. He drove an 18-wheeler on long cross-country trips and needed to use a dipstick to determine how much gas was left in the tank. There were a few markers that were particularly useful to know. For instance, he could easily use the stick to measure when he was halfway out of gas. But it is less straightforward to know when he had a quarter or 3/4 of the tank left. So the question is, how do you mark 1/4 tank using only the dipstick? I think this is a really interesting problem with a really nice physical motivation. And I've seen a few articles online trying to answer this question. And in particular, there's a great blog post from Wired magazine, which I'll link in the description and reference a few times within this talk. The Wired article in particular points out that this would actually make a great test question. However, every answer I've seen online to this question has only gone so far as to set up the problem and then give an approximate answer, rather than an exact one. In this talk, ideally, I'd like to arrive at an exact solution. It's hard to get started on this without a visual aid, so here's something I threw together in Desmos, an online graphing program. It's a cross-section of the fuel tank, gradually being filled and emptied, and we want to figure out where to position the line such that we have 1/4 of the circle shaded. In a perfect world, I'd give you audio snippets of the conversation between the trucker and the two MIT graduates, so that we could all go through the question together. But of course, that isn't fair use, so I'll instead summarize the insights from the episode. The first insight that the trucker offers is that the position of the vertical line is probably not 1/4 of the way up, and the brothers agree. If that's not obvious, think about what would happen if we filled up a cube rather than a cylinder. If it were a cube, the width of the container would not be changed as the gas level rose, but in our case, it does, so we have to be a little bit more careful. Next, the brothers realize that the height of the cylinder doesn't matter. This is an area problem, not a volume problem, so, as they say, you can do this in 2 dimensions. This is indicated in the visual aid I showed earlier, but the brothers didn't have one, so this is another important insight. And at this point, it is abundantly clear that we need to compute the area under a curve, so we know for a fact that this is an integral calculus problem. To restate the problem in more calculus terms, we're really asking, at what height above the bottom of a circle do you position a horizontal line such that the area below the horizontal line is 1/4 the area of the total circle? Again, it's useful to have a visual aid here, and frankly, I couldn't come up with a better illustration referenced in the Wired magazine article, so I posted that one here. We can imagine our area differential as these tiny infinitesimal rectangles that go from the bottom of the circle all the way to the location of the line. Now, what is the area of one of these rectangles? It will be the length times the width, where I have the width labeled as dy. So how do we get length times width in terms of one variable so we can do our integral? Well, we can use the equation of a circle, x² plus y² equals r², r being radius, to find the x value corresponding to an arbitrary y value on the circle. We can solve this for x, and then notice that since our x solution has a square root, there are 2 possible solutions. One of them will be positive, the positive square root, and one of them will be negative, the negative square root. And this makes physical sense in our case because every y value, or height, that we pick has 2 corresponding points on the circle, the left point and the right point. At that height, we can treat the length as 2 times the positive solution, where the factor of 2 comes from us accounting for both sides of the circle. Okay, so we have our equation for area with respect to one variable, which is the height of the line. All we have to do then is set the integral's bounds, and then set the expression equal to 1/4 of the circle's area, and then solve for that unknown height. For simplicity's sake, let's assume the circle has radius 1 and is centered at the origin. Then in terms of y, our area differential is given by dA equals 2 times the square root of 1 minus y squared dy. If y prime is the y-coordinate of that gas line, then we can integrate to solve for y prime like so. I'll cancel off the factor of 2 just for clarity's sake. Okay, now the result of this indefinite integral is 1/2 y square root 1 minus y squared plus arcsine y. So if we plug in our bounds and set that equal to pi over 8, we have the following. And a more simplified version of this would be this. This is a transcendental equation, the answer to which is about -0.404. Putting that in terms of the trucker's original problem, where the tank was 20 inches in diameter, we have that the dipstick should be marked 5.96 inches up. Now, about this last line, I glossed over it, but there are a few ways to evaluate this last line. I could, for instance, put it into Mathematica and use its solve function, or write a script to approximate the answer, or ask Wolfram Alpha to do it. But none of those are particularly satisfying for us. We want an analytical answer, something exact that we can express in pure numbers, like the square root of 2 or pi, or some combination of variables like those, or constants like those, rather. The fact remains, however, that this last line is transcendental, and so the closed-form analytic solution that we've been trained so hard as good calculus students to look for doesn't exist. I want to emphasize that there are many more practical ways of solving this problem. The hosts of Car Talk, when they realized the mess they're in, urged the trucker to find a fellow trucker, say at a truck stop, who had a quarter tank of gas, and then measure using the dipstick to draw the mark. This is probably what you or I would do if we had this real problem to solve. In the absence of a fellow trucker, you could also find some cylindrical object at home, like a water bottle. Fill it up a quarter of the way and then turn it on its side to measure the line. You just need to solve the problem for your mini cylinder and scale it up to the size of the gas tank. If you're like me and still want to approach this problem from a numbers angle, I've included this snippet of Mathematica on screen to solve that transcendental line numerically. You could also do as the Wired article suggested and write your own Python script to approximate the answer numerically. Here's a screen recording of me doing just that, and it still gets you the right answer of -0.404. So there's many ways to skin a cat here, but none of them have that satisfying oomph that I'd normally present in a video. And that's why I've sat on this for a year without ever making one, because it's a weird story to tell. We try working for a result and then we hit a wall. And if you get nothing else out of this video, I want you to understand that this is frustrating, but true about the mathematical world. There are so many mathematical problems like this that are motivated by very clear physical problems, those that start off with a promising, pretty solution but have to be solved in a more practical manner. For instance, the Kepler problem, widely considered to be the founding problem of analytical mechanics, doesn't actually have an analytical solution. And honestly, I wasn't totally comfortable with making this video until I learned just how many problems have to be solved in exactly the same way. I'll conclude with this quote from Andrei Kolmogorov, a mathematician notable for his contributions to such problems. The mathematicians always want that their mathematics should be pure, that is, strict and provable wherever possible. However, the most interesting and realistic problems could not usually be solved in that manner. Therefore, it is very important that the mathematician should be able to find the approximative, not necessarily strict, but effective ways of solving such problems. So the next time you run into a problem that you just can't solve with an elegant solution, don't feel so bad. Sometimes that's just how the universe works. Or at least that's how the math worked out.